So I see I wasn't recording, so I'm just going to go over the pages from the beginning just so it makes sense. So this is Math 175, Lesson 10, and we are doing the product and the quotient rule. So we start by recalling the addition rule, the sum rule. The derivative of the sum of two functions is the sum of the derivatives. We have the difference rule, or the rule for subtraction. The derivative of the difference of two functions is the difference of the derivatives. And the next thing we want to consider is the product rule. How do you find the derivative of the product of two functions? And it's not the most obvious answer. The most obvious answer would be to say, well, the derivative of the product is the product of the derivatives. But that is false, so I've crossed it out. The product rule is in some sense is more complicated and maybe therefore more interesting. If you have the product of two functions, f and g, the derivative of the product, you take the derivative of the first factor times the second, plus the first factor times the derivative of the second. And then we have a number of examples. Suppose we take the product function x sine x. So we have f of x equals x and g of x equals sine x. The product is x sine x. The derivative of x sine x is the derivative of x times the sine plus x times the derivative of the sine. The derivative of x is 1 and the derivative of the sine is the cosine. So by the product rule, the derivative of x sine x is sine x plus x cosine x. Another example, suppose I take h of x to be this polynomial, which is a product of two other polynomials. It's a product of the quadratic 3x minus 2x squared times the linear polynomial 5 plus 4x. So by the product rule, the derivative is the derivative of this term, which is 3 minus 4x times the second term, plus the first term times the derivative of the second term, and the derivative of 5 plus 4x is just 4. So this is what we get. If you multiply these together and collect the terms, you get this quadratic polynomial. Now, we have an independent check of this because, in fact, we could just multiply these two factors together. It's a product of two polynomials. When you multiply them, you get, just multiplying it out, you get 15x plus 2x squared minus 8x cubed. When you differentiate, you see you get exactly the same thing. So we solve one problem in two different ways, and as must always happen, you get the same answer. Because the answer doesn't depend on the method, it depends on the problem. The next example is y equals x e to the x. The derivative is the derivative of x, which is 1 times e to the x, plus x times the derivative of e to the x, which is e to the x. So you get e to the x plus x e to the x, and if you factor out e to the x, it's e to the x times 1 plus x. The fourth example was y equals 2x cosine x minus 2 sine x. First of all, this is a difference of two functions. So the derivative is the derivative of the difference. Now this is just 2 sine x. The derivative is 2 cosine x. This first term is a product of two other functions, 2x and cosine x. And when you differentiate by the product rule, the derivative of 2x is 2, so we get 2 cosine x. The derivative of cosine x is minus the sine. So this gives us minus sine x times 2x. The cosines cancel, and that's what you get. I just did it again. Okay. And the last example was the function 3x minus 1 over the square root of x, which is a product of 3x minus 1 times 1 over the square root of x. Now, in this form, it looks like a quotient rule, which I'll do in a few minutes, but I haven't done it yet. But we can still solve this problem because 1 over root x is 1 over x to the 1/2, which is x to the minus 1/2. So this product is really 3x minus 1 times x to the minus 1/2. And when you use the product rule, the derivative of 3x minus 1 is 3 times x to the minus 1/2. And 3x minus 1, what's the derivative of x to the minus 1/2? You use the power rule. You get minus 1/2 x to the minus 3/2. And then you can simplify it in various ways and you get a nice answer. But, that's what it is. Any questions so far? Now, you might be curious, where does the product rule come from? Why do we have this strange formula, which you might not guess a priori? So let me give you a proof of the product rule directly from the definition of the derivative. So this is the proof. We want to find the derivative with respect to x of the product of these two functions. So the definition says this is the limit as delta x goes to 0 of f of x plus delta x, g of x plus delta x, minus f of x times g of x over delta x. That's the definition of the derivative. And I want to play with this a little bit. I have f of x plus delta x, g of x plus delta x. And I have a minus f of x, g of x. And I left a big space in the middle because I'm going to add 0. Well, you can always add 0. And I'm going to add 0, but in a funny form. It's because I'm going to put in minus f of x plus delta x, g of x, plus f of x plus delta x, g of x. So I added and subtracted the same thing, like James, I've added 0, and you can always add 0. Now I write this as a sum of two terms. This is the limit as delta x goes to 0. From these first two terms, this term and this term, I can factor out an f of x plus delta x. So I have g of x plus delta x minus g of x. And then from the second two terms, I can factor out a g of x. I have f of x plus delta x minus f of x, all times g of x. So I'm just rearranging this. And I can write the limit as of the sum as the sum of the limits. This is the limit as delta x goes to 0 of this first term, f of x plus delta x times g of x plus delta x minus g of x over delta x, plus the limit as delta x goes to 0 for the second term, f of x plus delta x minus f of x over delta x times g of x. So all I did is basically high school algebra manipulations, but there's an idea involved. It's not just the manipulation, there's some cleverness here. Because all of these limits exist. F is continuous, so as delta x goes to 0, f of x plus delta x has the limit f of x. And as delta x goes to 0, this is exactly the definition of the derivative of g. That's g prime of x. And on this side, this limit is the derivative of f times g of x. And that is the whole proof. It's one long line. It's very pretty. That's the whole proof. Do we have any questions about this? All right. So that's the proof of the product rule. So the product rule is a little more complicated than the addition or subtraction rules for derivatives. And the quotient rule is a little more complicated than the rule for the derivative of the product. So suppose we have two functions, f of x and g of x, and g of x isn't equal to 0. So you can divide by it. So if g of x is non-zero, you can divide by it. And I can write down a rule for the derivative of the quotient of two functions. So this is much more complicated than the product rule, and it's the following. So it's going to be a quotient, and the denominator of the derivative of the quotient is the quotient squared, g of x squared. And in the numerator, we have the derivative of f times g of x minus f of x times the derivative of g of x. And the order is very important. If you reverse the order, you're off by a factor of -1. Okay? So if you have the quotient of two functions, f over g, and g is not 0, that's the point where you're taking the derivative. The derivative of the quotient f over g, it's f prime g minus fg prime over g squared. Right? So that is the quotient rule. And I'll do a lot of examples, and then I'll prove it. So, examples. Suppose we have the function 5x minus 2 divided by x squared plus 1. So this is of the form f of x over g of x. This is some function y. The numerator, f of x, is equal to 5x minus 2. The denominator, g of x, is x squared plus 1. If f is 5x minus 2, f prime of x is 5. If g is x squared plus 1, g prime of x is 2x. What does the quotient rule say? The quotient rule says that the derivative of this quotient, 5x minus 2 over x squared plus 1, it's, let me write it out in excessive detail. It's the derivative of the numerator times the denominator minus the numerator times the derivative of the denominator over the denominator squared. So this is something over x squared plus 1 squared. The derivative of 5x minus 2 is 5. So 5 times x squared plus 1 minus 5x minus 2 times the derivative of x squared plus 1, which is 2x. So this is equal to 5x squared plus 5 minus 10x squared plus 4x over x squared plus 1 squared. And 5 minus 10 is minus 5x squared plus 4x plus 5 over x squared plus 1 squared. Oops, did I do something wrong? Minus 5x squared plus, no, looks good. That's what it is. Okay. So this is our first example of the quotient rule. And it takes a little bit of calculation to compute these derivatives, but not too much.
Professor, where did the 15 come from? I thought it was 5.
Plus 5. Just
Oh,
plus
okay.
5. Yeah. By the way, for those who keep track of these things, the first midterm exam is 2 weeks from today. So 9 to 11, 2 weeks from today, or 9 to 10:40. But we'll talk about more. We'll talk more about the exam later. All right, let's keep doing some examples. We just want to follow some of the examples in the book, because then when you study at home, I think it makes it easier. So problem is stated like this. Find an equation of the tangent line to the graph of the function f of x equals 3 minus 1 over x over x plus 5 at the point minus 1, 1. By the way, this just checks something. If you evaluate this function at 1, you get 3 minus 1 over 1 plus 5. Which is 2. 3 minus 1 is 2 over 6. Is 1/3. So something is wrong. So the book is wrong here, because when you plug x equal 1 into this, you get 2, you get 1/6. You don't get, oh, sorry, f of minus 1. I wrote down the wrong thing. Let me see if that makes a difference. So f at minus 1 is 3 minus 1 over minus 1 over minus 1 plus 5. This is 3 plus 1 over 4, which is 1. So this is okay. So when x is equal to -1, y is equal to 1. So this is a function. It has a graph. It's defined everywhere except at -5. Because there the denominator would be 0. So there's a vertical asymptote at -5. And we want to find the equation of the tangent line, which means we have to compute the derivative f prime of x. Before I do that, we can simplify this function a little bit to make the work easier. So we have f of x is 3 minus 1 over x plus 5. If we multiply the numerator and the denominator by x, you get 3x minus 1 in the numerator and x squared plus 5x in the denominator. This is a little bit easier to differentiate. So the derivative with respect to x of f of x is equal to, we take the denominator and we square it, and in the numerator is the derivative of the numerator. Let me just write this all out. 3x minus 1 prime, I just mean the derivative, times x squared plus 5x minus 3x minus 1 times x squared plus 5x prime. Derivative of 3x minus 1 is 3 times x squared plus 5x minus 3x minus 1. And what's the derivative of x squared plus 5x? It's 2x plus 5. Now, we really shouldn't leave it like that. Let's simplify this. This is 3x squared plus 15x minus, when you multiply this together, you get 6x squared minus 2x plus 15x is plus 13x minus 5. So this is equal to minus 3x squared plus 2x plus 5 over x squared plus 5x all squared. That's the derivative, f prime of x. If we evaluate this at -1, you get minus 3 minus 2 plus 5 over 1 minus 5, which is minus 4 squared. This is 0, right? 5 minus 5 is 0. If it's 0, it means that the tangent line has slope 0, so it's horizontal. So the equation of the tangent line, if it's the horizontal line through the point -1, 1, it's just the line y equals 1. So that's the equation of the tangent line. If this were the graph of the function, and this the point -1, 1, it's the horizontal line y equals 1, that's the tangent line. All right. Any questions about these? Let's look at some more examples. So let's recall the power rule. I said this is true for all exponents, but I only proved it for n a positive integer or 0. But now from the quotient rule, I can just derive the power rule for negative exponents. Because suppose I want to differentiate 1 over x to the n, where n is positive. So for this, I can use the quotient rule. This is the denominator squared, the derivative of the numerator times the denominator minus the numerator times the derivative of the denominator. The derivative of 1 is 0, so that term disappears. And the derivative of x to the n is minus n x to the n minus 1 over x to the 2n. That's minus n times 1 over x to the n plus 1. Or minus n x to the minus n minus 1. So this says the derivative of x to the minus n is minus n x to the minus n minus 1. That's exactly this rule with n replaced by n minus 1. So if you actually just prove the power rule for positive integers from the quotient rule, we get the derivative of x to a negative integer. We can also now get the derivatives of the other 4 remaining trig functions. Remember, we proved the derivative of the sine of x is the cosine of x, and the derivative of the cosine of x is minus the sine of x. But what about the derivative of the tangent of x? Well, we recall tangent is sine over cosine. So we can use the quotient rule. This is cosine squared x in the denominator. The derivative of the sine, which is the cosine, derivative of the numerator gives us the cosine times the denominator, minus the numerator times the derivative of the cosine, which is minus the sine. So we get cosine squared x plus sine squared x over cosine squared x. But we have to always remember the fundamental trig identity. Cosine squared plus sine squared equals 1. So this is 1 over cosine squared x, or 1 over the cosine squared. What is 1 over the cosine? It's the secant. So we have now the formula for the derivative of the tangent. It's secant squared. So we know the derivative of the sine and the cosine. We now know the derivative of the tangent. Let's work out the derivatives for the cotangent, the secant, and the cosecant. Because these come up all the time and we need to know them. So the derivative of the cotangent of x, cotangent is cosine over sine. This is a quotient rule problem. You get sine squared x in the denominator. In the numerator, derivative of the cosine, which is minus the sine, times the denominator, minus the numerator, times the derivative of the denominator. So what we get is sine squared x minus sine squared x minus cosine squared x, which is minus sine squared plus cosine squared x. This is minus 1 over sine squared x, or minus 1 over sine x squared. What is 1 over sine x? It is the cosecant. So the derivative of the tangent is the secant squared, and the derivative of the cotangent is minus the cosecant squared. Any questions about these? Okay, we're left with the secant and the cosecant. What is the derivative of the secant of x? Well, the secant is 1 over the cosine. So by the quotient rule, we get cosine squared x in the denominator. In the numerator, we get the derivative of 1, which is 0, minus the derivative of the cosine, which is minus the sine. Minus times minus is plus, which I can write as sine x over cosine x times 1 over cosine x, which is the tangent of x times the secant of x. So the derivative of the secant is tangent times secant, or secant times tangent. It's really your choice how you write it. Finally, the last and the sixth trig function is the cosecant of x. The cosecant is 1 over the sine. By the quotient rule, we get a sine squared x in the denominator. In the numerator, derivative of 1, which is 0, minus the derivative of the sine, which is the cosine. So what we have is minus cosine x over sine squared x, or sine x times sine x. This is the cotangent, that's the cosecant. So this is minus cotangent of x, cosecant x. And now we have all 6 trig functions. All 6 trig functions. All right, any questions about this? Now, let's go back for 1 second. This is the quotient rule. I just wrote it down. Maybe you believe me, but it's natural to ask, where did such a weird, complicated expression come from? How do we know this is true? You can calculate this right-hand side, but how do we know this is truly the derivative of the quotient? Right? So that's something that does require a proof, and I shall now, before your very eyes, prove it. So what I need to do is give a proof of the quotient rule. So we have the quotient of 2 functions, f of x over g of x, and I want to find the derivative. So again, we're just going to use the fundamental definition of the derivative. This is the limit as delta x goes to 0 of this quotient evaluated at x plus delta x minus the quotient evaluated at x divided by delta x. And then here we really need to be able to do high school algebra. Right? This is a compound fraction. Let's simplify it. Let's multiply the numerator and the denominator by g of x times g of x plus delta x. When I do, the g of x plus delta x cancels here. I get f of x plus delta x times g of x. Here, the g of x's cancel. I get f of x times g of x plus delta x. And notice this minus sign, that's important. And I'm going to do something analogous to what I did when working out the product rule. I'm just going to add 0 to the numerator. I'll put it in here. And my 0 is going to be of the form minus f of x g of x plus f of x g of x. So I just added and subtracted the same thing. And let me rearrange this numerator. I can factor a g of x out of this. And from these two terms, I can factor out an f of x. So this minus this, or if I put a minus sign here, it's this minus this. Aha. So let's write this as two limits. This is the limit. Delta x goes to 0. I have f of x plus delta x minus f of x over delta x times this over this, which is 1 over g of x plus delta x. Something doesn't look right here, so let me just double check what we've done. This minus this, so it's this times this minus this times this over this. And if I add and subtract this, I get this over this. I'm going to worry about this in a minute. Something doesn't look quite right. Minus, the limit is delta x goes to 0. Here I have f of x, g of x plus delta x minus g of x over delta x over g of x plus delta x. Let's see. Oh, sorry. This is okay. Let me just not cancel. G of x, g of x. And so what happens is delta x goes to 0. This goes to f prime of x times g of x over g of x times the limit of this gives me a g of x squared minus this, which is f of x, g prime of x, again over g of x squared. So we have the same denominator, g of x squared, f prime of x, g of x, minus f of x, g prime of x. So that's perfect. Well, in advanced calculus, you really need to know the details of these proofs. In beginning calculus, math 175 and 176, you don't, but it's good to see it, and it's in the text, and you'll have a much deeper understanding of what's going on if you can work through the proofs and understand them. Mhm. Any questions of this? All right, so we're almost done with this lesson. There's one last thing to do. And let's just say, because finding derivatives, which is differentiation, because differentiation is fun, we want to do it over and over. And what do I mean by that? Well, suppose I have the function f of x equal x to the fourth. Let's find the derivative of f of x. It's 4x cubed. Well, good. If we like to differentiate, let's take the derivative of the derivative. That's the derivative of 4x cubed. That's 4 times 3x squared, or 12x squared. When you differentiate twice, we call this the second derivative of the function. And we write this usually as something like d2f dx squared. Or we can write it as f double prime of x. All right. So if you take this function, you differentiate it once, you get this. If you differentiate the derivative, you get this. Let's keep going. Suppose I want to take the derivative of the second derivative. So that's the derivative of 12x squared. That's 12 times 2x, or 24x. So we call this the third derivative. Write it like this, or f triple prime of x. And then it's natural. What would the fourth derivative be? It would be the derivative of the third derivative. That's the derivative of 24x, which is 24. And the fifth derivative would be the derivative of the fourth derivative. The fourth derivative is just the constant 24, and we get 0. So if you enjoy doing derivatives, you can just do it a lot. Differentiate x to the fourth, you get 4x cubed. To get the second derivative, you differentiate again, you get 12x squared. The third derivative, 24x. The fourth derivative, 24. Fifth derivative, 0. And you can keep on differentiating, but once you get to 0, all the derivatives are 0. Now, by far, the most important derivatives, and the ones we will use a lot, are the first derivative and the second derivative. And in science, you learn about position of a particle, velocity, which is the rate of change of the position, and what's called acceleration, which is the rate of change of the velocity. So if s of t equals position of a particle at time t, if you differentiate position, this by definition is the velocity, v of t. Right? So velocity is the first derivative of position. What is called the acceleration, a of t, is the derivative of the velocity. But velocity is the derivative of the position. So this means the derivative of the derivative, the second derivative. So we use these definitions in calculus all the time. If you have the position of a particle at time t, the derivative of the position is the velocity, and the second derivative of position is the acceleration. So that's where we are. Okay. Let me pause for a minute just to note the attendance, which I like to do periodically. So, who is here today? Said, Reyes, Angela Thomas, Anthony Calderon, Augusto Garcia, Carlos German, Elijah Atkins, Eric Aquila, Jocelyn Gonzalez, Jingwen Guan, Mohammed Osman, Nina Noble, Rachel Scott, Raphael Goulart, Shakira Seymour, Zakra Khan, and that seems to be it for right now. Okay, anyone I missed? All right, well, let me do one or two more problems, though what I prefer doing when it's possible is to answer questions you have about problems you found complicated or hard to do. But let's take a look at some of these problems. Well, from the homework, this is problem 29. I did this earlier using the product rule, but let me do it again using the quotient rule. So this is f of x equals 3x minus 1 over the square root of x. So I want to think of this as a quotient. F prime of x will be what? It's the denominator squared. And then on top, the derivative of the numerator, which is 3, times the denominator, minus the numerator times the derivative of the denominator. Now the denominator is the square root of x, which is x to the 1/2. So the derivative of the square root of x by the power rule is 1/2 x to the 1/2 minus 1, which is 1/2 x to the minus 1/2, or 1 over 2 times the square root of x. So it's 3x minus 1 over 2 times the square root of x. So if I put this over, if I multiply numerator and denominator by 2 root x, in the bottom I get 2 root x times root x squared, which is x. 2 root x times 3 root x is 6x minus 3x minus 1. So this looks like 3x plus 1 over 2x to the 3/2. when I did this earlier on page 4, I did it using the product rule, but of course you get exactly the same answer, which has to be the case. Suppose I wanted to do, this is number 48, it's not one of the homework problems, but it looks interesting. Y is secant x divided by x. So dy dx, we have x squared in the denominator. In the numerator, we have the derivative of the secant times the denominator minus the secant times the derivative, the derivative of the numerator, secant times the denominator, minus the numerator times the derivative of the denominator. The derivative of the secant is secant times the tangent times x minus secant x times 1 over x squared. That's what it is. This is number 105. We want to yeah, I won't do that one. I'll say that. Do one more. So this is number 69. So we have the function f of x equals x minus 1 times e to the x. When you let f of x equal 1, f of 1 is 1 minus 1 e to the 1, that's 0. And we want to find the tangent line to the curve going through the point 1, 0. So we have some curve. It goes through the point 1, 0. What's the tangent line? Well, the slope of the tangent line is the derivative. By the product rule, the derivative, because this is a product of two functions, the derivative of x minus 1 is 1 times e to the x plus x minus 1 times the derivative of e to the x, which we saw was e to the x. So we have e to the x plus x e to the x minus e to the x. These cancel. This is just x e to the x. So f prime of 0 is 0. Well, it's not very interesting because, again, the tangent line is horizontal. So the tangent line is just y equals 0. Yeah, that's pretty boring problem. Okay. Let me just say a word about the exam in 2 weeks. So the way the exam will work is the following. A little bit before the class starts, the exam will be designed to be really an hour exam, to take an hour. But you will have the whole hour and 40 minutes of the period to do it because it takes some time, I know, to, after you've written out the solutions, to convert it to a PDF file and upload it to the website. So you will do the exam at home, obviously. You will scan your handwritten pages to convert it to a PDF file. you'll go to the Blackboard website for the class, and in the assignment section, there's exam 1, and you will upload the PDF file to Blackboard. You have to show all of your work. If the problem is to, if you just write down the answer, that's wrong. Unless it's like a one-line thing, like if the question is, what is the derivative of x squared? The answer is 2x. You write that down and you're done. But if you just write down the answer for a problem that's not obvious just by looking, you won't get any credit. You have to show your work. That's the way exam is. So, and there will be, we have a session just for review before the exam. There are probably 10 questions, it's a simple exam. 10 questions, that's it.
Do we need to open the video to show ourselves?
Excuse me?
Do we need to show ourselves from the video?
Show yourself?
Yeah.
Why?
Okay.
I mean, you mean, do I want to be able to see you working at your desk?
Yeah.
Oh, that's pretty clever. I never thought of that.
So it's just gonna be on the website when the class starts, right?
Right. It'll be on the website, and I will also email it to you, through Blackboard.
Okay.
So you'll have 2 ways to access the exam, and you write out the answers. It's an open book exam. You can use your book. And you write out, which means I'm not going to give you any problems from the book. Will there be a practice exam? Well, there will be a review sheet, and the review sheet is like the practice exam. Okay. All right. That's it for today then.
Professor,
Yes.
I saw the YouTube that you will upload for the lessons 8. I'm not sure is it the right one, but I saw like
Okay. I'll go and double check that.
424, yeah.
Right. So I'm also teaching a course in partial differential equations, and maybe I uploaded the PDE lecture instead of the calculus one.
Yeah, I saw PDE also.
Yeah, that's partial differential equations. That's the title, the name of the course.
Oh, okay.
Yeah. So you said that was lesson 8?
Yeah, lesson 8.
Okay. I'll go fix that right now. Thank you.
Okay.
Okay. See everybody. Well, I won't see you. I'll see your name on the participants list. Next Monday. Have a good weekend all. Bye.
Bye, Professor.
Bye.